Hello everyone. In today's lesson, we're going to be covering section 5.5 on the normal approximation to the binomial distribution. A normal distribution can be used to approximate the binomial distribution when it would be impractical to use the binomial distribution to find the probability. An example of this might be if you have a very large sample size, right? Think about when we were doing our probability trees, and we might have something like flipping a coin. So we'd have that we could get heads or tails. We could get heads or tails. We could get heads or tails, and then we could keep doing this. And what's happening is as we get more and more and more trials, this is going to become more and more difficult to sort of map out using something like a probability tree. Similarly, whenever we are doing our binomial probabilities, we had so on and so forth. We had, for example, the probability that x was less than 15, let's say. If I wanted to do something like this, I would need to find the probability of 0 plus the probability of 1 plus the probability of 2, so on and so forth, all the way up to, in this case, the probability of 14, because this is discrete data, therefore probability less than 15 would be probability less than or equal to 14. So this would be a lot to calculate, but doable. And we talked about some methods we could use, for example, using the complement. If n was only equal to 20, then it might be beneficial to use the complement. But what if we had a total of 100 trials? Well, then your option would be to do 15 calculations or to do 86 calculations, something like that. But what if it was n was 1,000 or 100,000 or 1,000,000? And you might have this case where you might have 100,000 trials where you want to know what's the probability of getting less than 40,000 of them for some example. This would be infeasible to calculate using binomial. Also, if you go into your calculator and even just try to calculate certain big binomial probabilities, right? Because if you remember the formula for a binomial probability, so probability that x equals x is equal to n choose x, p to the x, 1 minus p to the n minus x. And this n choose x is going to be n factorial over n minus x factorial x factorial. Go into your calculator and try to put in like 1,000 factorial and see what happens. I guarantee that you will probably get an error. Even using more advanced tools like R or Python, something like that, these factorials can grow very fast and become very difficult even for computers to work with. So a lot of times we're going to want a method that we can use when using the binomial probability, which is the actual probability, is infeasible. So what we're going to do is we're going to use an approximation. The way that this works is as our sample size increases, what's going to happen is our binomial probability is going to start to look like a normal distribution. And I'll show you examples of this in another video. Something like this, where then we can overlay a normal distribution on top of it to get an approximate probability. Now, a couple things you have to consider, though, when you're doing this is that it's not going to be an exact probability, right? Because just looking at the way I drew it, we're going to have some parts that are undercounted, and you're going to have other parts where it's overcounting. So in the end, it's not going to be the exact probability. If you use the binomial probability, you will get the actual probability. This is an approximation. Now, we talked about the fact that if we have a large enough sample size, well, how do we know if we have a large enough sample size? Well, for this class, we're going to be checking two assumptions to see if we have a large enough sample size. So our assumptions will be if n is greater than or equal to 5, if np is greater than or equal to 5, and if nq is also greater than or equal to 5. Now notice I used the word and here. This means that both of them must be true. If np is greater than or equal to 5, but nq is not, you don't have a large enough sample. If nq is greater than or equal to 5 and np is not, you don't have a large enough sample. If both of them fail, you definitely don't have a large enough sample. But if both of them are true, that NP is greater than or equal to 5 and NQ is greater than or equal to 5, you have enough data to be able to use the normal approximation. Now, I want to point out, this is sort of a rule of thumb. You may see in some other texts or books that they use NP greater than or equal to 10 and NQ greater than or equal to 10. Now, we might wonder, why do we use this sort of number, right? It's sort of arbitrary, but the idea is that if you have very centered data, which is symmetric about some mean, then you don't need a very large sample size for this to be true. But the more that it's skewed, the more that data you're going to need for it to be true. So let's look at what this means. Let's say, for example, that we have n equals 10 and p equals 0.5, right? So with p equals 0.5, this means that I would expect, my expected value would tell me that I expect 5 on average, which the next lower numbers from there being 6 and 4, next numbers from there. And basically you should automatically kind of get this very normal looking graph. And if we did our test, NP would equal 10 times 0.5 equals 5, which is greater than or equal to 5. And if we did NQ, well, if P is equal to 0.5, then Q is going to be equal to 0.5. So 10 times 0.5 would also give me 5, which is greater than or equal to 5. Therefore, with P equals 0.5, all we need is a sample size of 10. But let's say instead we had P equals 0.9. Well, in this case, if we do NP, this would be 10 times 0.9, which would be equal to 9, which is greater than or equal to 5. That succeeds. But NQ would be 10 times 0.1, which would give us 1, which would not be greater than or equal to 5. So what this means is, because when I have P equals 9, what's happening is I'm actually getting a skewed distribution. If I were to try to graph over this, it would look something like this. It's skewing to the left. So what we need to do is we need to increase our sample size. So if P equals 0.9, I would need to figure out what size sample would I need to make this second statement true. And in this case, it would be N equals 50. So now if we did this again, NP equals 50 times 0.9, and NQ will equal 50 times 0.1, and we would get 45 for the first one, which is greater than or equal to 5, and we would get 5 for the second one, which is greater than or equal to 5. So now with this, I have a large enough sample to account for this skew that's going on when I do this. So how do we actually do this? Well, first we're going to start with our z transformation that we use whenever we're doing normal distribution, which is going to be z equals x minus mu over sigma. Now, you may know, because we're using a binomial probability, that we don't have mu and we don't have sigma, but we did talk about how we can find those values. So when you have a binomial, your mu is just going to be your expected value of n times p. Your standard deviation is going to end up being the square root of n times p times q. And these are values that we will have in a binomial probability problem. Let's say that this graph here represents our binomial probability. And we'll say that this value here, if I did n times p, I would get 7. Now, if I were to find, using a binomial, the probability that x is greater than 9, let's say. Well, if this is 7, this is 8, this is 9, 10, 11, 12, 13, and 14. So for a binomial probability, if I said probability x is greater than 9, the first thing we have to do is we have to get it in terms of greater than or equal to. Because remember, this is in the discrete space, meaning that there's nothing between 9 and 9 is not included. So this would actually be the probability that x is greater than or equal to 10. So in that case, I would be finding this probability. I'd find the probability of getting a 10, the probability of getting an 11, getting a 12, a 13, and a 14, let's say. So this is probability of 10, 11, 12, 13, and 14. Now, if I were to overlay a normal distribution on top of this, right, this is for my binomial case, Well, for the normal distribution, this is continuous data. So when I say the probability is greater than 9, this is equivalent to saying probability of x greater than or equal to 9. So in this case, what would happen is that I would actually, if I just directly did this, I would find the probability to the right of this point, which of course would count too much of the data. So first thing we need to do before you do any calculations for binomial is you always need to get it in terms of greater than or equal to before you start doing your normal approximation. So now in this case, I would have that it's the probability of x is greater than or equal to 10. So the first step is always get it in terms of or equal to. So if you have greater than, you need to get it in terms of greater than or equal to. If you have less than, you need to get it in terms of less than or equal to. Once you've done that, you can begin to do your normal approximation. But we still have a problem, because if you look at what a normal distribution would find, is that it would say, okay, well, I want everything greater than 10, which would be all of this. But you might see that what happened here, this part right here, we missed half of our 10 category for our binomial probability. So we actually have to do is what's called correction for continuity. So we have to do correction for continuity. And what this means is that we are going to actually have to shift either to the left or to the right by 0.5 in order to account for the fact that when we switch from our binomial probability to our normal probability, we're actually going to be splitting one of the categories, whatever group we're in half, and we have to account for that by adding or subtracting 0.5. So let's look at the different cases that we might encounter when doing this. When we're doing our correction for continuity, our couple cases would be something like this. Let's say that we have, I'll go back to what we had last example. We had probability x is greater than 9. Well, first thing, we're going to convert this to or equals to. So because this is binomial, right, this is discrete data, this is going to be equivalent to probability x is greater than or equal to 10. So now what we're doing is we are going to find the probability that x is greater than or equal to 10. If I want to correct for continuity, because if you remember around this 10, there should be a box which represents the probability. I'm missing the left half. I need to subtract 0.5. So this would become probability of x greater than or equal to 9.5. So when you have greater than or equal to, you are going to subtract 0.5. And this is basically because what we're doing is when we're looking greater than, we are splitting this 10 and we are doing everything to the right of it. We need to count what's to the left on that 10 value, so therefore we have to subtract 0.5. Case 2 would be, what if we had something like the probability of x is less than 9? Well, in that case, again, this is discrete. First, we have to get it in terms of or equal to, so this would be probability of x less than or equal to 8. And in this case, we have some 8 where our binomial probability would be the point around 8, and then of course everything to the left of it. So we're finding when we do our normal is we're doing everything to the left of where 8 actually is. So what we need to do is to include this right half of the box is we need to add 0.5. So this would become probability x is less than or equal to 8.5. So if you have less than or equal to, you need to add 0.5. The third case is what if we have the probability of x between two values. Let's say that x is between 6 and 9. Now I've already put it in terms of or equal to, but if it wasn't, you would just do the same steps you do to get it into or equal to statement. So in this case, we would have the values 6, we would have the values 9, and we want to find the probability between them. Now, when we talked about how to find these kind of probabilities, you know that we need to find the probability to the left of the larger value minus the probability to the left of the smaller value. Cut this out and you'll have the probability between them. But we also have to count for correction for continuity, because when we're finding the probability to the right of 6, we're missing out on this half of 6. When we find the probability to the left of 9, we're missing out on this half of our probability. So in this case, what you have to do is you have to subtract 0.5 from the 6. So this would be 5.5 is less than or equal to, x is less than or equal to, and add 0.5 to the 9. So you're going to subtract 0.5 from the lower value. You're going to add 0.5 to the upper value. And then the last case is, what if we wanted to find the probability that something is equal to, right? So probability of x equals 5. Well, we discussed the fact that for a binomial, I could find this. I could easily calculate the probability that x equals 5. But for normal probabilities, I can't do probability x equals to something. So what we're going to do is we're going to turn this into an interval by considering the fact that if I have this distribution, let's say 5 is over here, that I am going to go out to the left 0.5 and to the right 0.5 to get this interval. So this is going to be probability of 5 minus 0.5, or 4.5, is less than or equal to x is less than or equal to 5 plus 0.5, or 5.5. So in this case, you are going to add and subtract 0.5. So if you have greater than or equal to, you minus 0.5. If you have less than or equal to, you add 0.5. If you have that it's between two values, you subtract 0.5 from the lower value, you add 0.5 to the upper value. And if you have it as equal to, you both add and subtract 0.5 to the value. Now, you might wonder, is there an easy way to kind of remember what to do? And the answer is yes. Do whatever would make your interval bigger. So for example, if I'm looking to the right, what would make this interval bigger? Well, I don't want to go this way, I want to go this way, which means I'm going to subtract 0.5. If I have less than or equal to, then in this case, if I want to make it bigger, I would add 0.5. If I have an interval between two values, how do I make this bigger? I subtract 0.5 from one end, I add 0.5 to the other end to make it a bigger interval. And the same thing, even when it's just a single value, how do I make this bigger? I go minus 0.5 and plus 0.5 to create an interval from it. Looking at this slide, you can see an example of what we mean whenever we're doing our correction for continuity. You can see in the upper graph that when we did our normal probability, how it splits that box in half. And with correction for continuity, we take that into account. You can also see our conversion process. Case 1, where we had greater than or equal to, we subtract 0.5. Case 2, where we have less than or equal to, we add 0.5. Case 3, where we have between A and B, we subtract 0.5 from A, we add 0.5 to B. And last case, when we have that x is equal to some value, you add and subtract 0.5 to that value. So now let's recap what we've talked about and sort of go through the steps that we'll take when doing a binomial probability problem. So the first thing is, if the number of trials in and the probability of success of each trial P is given, then you should recognize that it's a binomial probability problem. Note that this also means that we do have to determine what the mean mu is and also what the standard deviation sigma is. First thing you're going to do before you do any calculations is check your assumptions. You have to check that NP is greater than or equal to 5 and NQ is greater than or equal to 5. If this fails, you cannot do a normal approximation, and you are going to have to just use a binomial probability like you learned in Chapter 4. Once you've checked your assumptions, you know that you can calculate your binomial probability by using an approximation from a normal probability. The next step would be calculate your mu, calculate your sigma, because you know you're going to need them anyway. Once you've done that, I would actually focus first on, when you set up your problem, get it in terms of less than or equal to or greater than or equal to. So convert from less than to less than or equal to, or greater than to greater than or equal to. If you have that it's between two values, this is the same step. If you have that it's between 5 and 7, but it's greater than 5 and less than or equal to 7, you would have to convert the greater than 5 to greater than or equal to 6. So get it in terms of or equal to. Once you've done that, you do your correction for continuity. If it is less than or equal to, you need to add 0.5. If it's greater than or equal to, you need to subtract 0.5. If it's between two values, you subtract 0.5 from the lower value, add 0.5 to the upper value. If it's equal to, you add and subtract 0.5. Next thing then is you set up your problem just like you would any other probability using a normal probability function, which is probability of x greater than or less than or equal to some value. You are then going to convert it using your z transformation, plugging in your mu and your sigma that you calculated. You're going to get it in terms of z, and once you're at that step, it follows the exact same steps it always does once you get your probability of z. Let's do some examples to kind of check out how we would do this. A survey reports that 53% of college students use Google as their search engine. 100 students at a college were randomly selected and were asked whether they use Google as their search engine. Using normal approximation of binomial probability, what is probability that more than 66 will say yes? So we want to know, what is the probability that x is greater than 66? We want to know that more than 66 said that they use Google as their search engine. Now, looking back at this problem, it reported that 53% of college students use Google. That's our probability of success. Our success, P, is equal to 0.53. This is our given information. They sampled 100 students, so that's our n. N equals 100. Now, because we know what P is, 0.53, we also can figure out what Q is. Q is just 1 minus P, so it's going to be equal to 0.47. We need to check our assumptions, because if we needed to solve this without the normal approximation, we would have to find the probability of 67, 68, 69, 70, and do that all the way up to the probability of 100. And notice doing the complement wouldn't help in this case, because in this case, the complement would be less than or equal to 66. You'd have to do 0, 1, 2, 3, all the way up to 66. So let's check our assumptions. We have that NP is equal to 100 times 0.53, which is equal to 53. That is greater than or equal to 5, so we're good for that one. NQ is going to be equal to 100 times 0.47, which is equal to 47, which is greater than or equal to 5, so we're good for that one. So that means we can do our normal approximation. So now at this point, you could figure out what your mu and what your sigma is going to be. Well, mu we actually already found, because mu is just equal to NP. And we actually found that while we were checking our first assumption. So we know that mu is equal to 53. Sigma is equal to the square root of n times p times q, which is going to be equal to 100 times 53 times 47, and then you're going to take the square root of that, and you are going to get 4.99. Now let's focus on our probability. We have probability x is greater than 66. So the first step we want to take is we need to get this in terms of greater than or equal to. So because it's greater than 66, that means it's everything above 66, not including 66. And there's nothing in between 66 and 67 because this is discrete data at this point. At this point, we're still in the discrete space. So that means we're going to move it up to probability of x greater than or equal to 67. Now we need to do our correction for continuity. So remember, our correction for continuity, if we were finding this probability here, we have some value 67, and we're looking at what is the probability of something greater than or equal to this. So in order to make this interval bigger, what I would need to do is I need to go to the left, which means I need to subtract 0.5. So this is going to be equal to the probability that x is greater than or equal to 66.5. Now, I do want to caution you while we're at this point. If you look at this, you might see that we went from 66 up to 66.5. Do not do this, because first thing you need to get it in terms of or equals to, because what you're doing is you're subtracting 0.5 from the probability we're actually looking for. So a lot of examples, we will have it in terms of greater than or less than, and then you will convert it to or equals to, and then you'll do your correction for continuity. If you get in the habit of going straight from x is greater than 66 to x is greater than or equal to 66.5, if I gave you the problem in terms of or equals to, you would be going in the wrong direction and you would be adding to the wrong value. So always just think of it in terms of order. Is it less than or greater than? Convert it to less than or equal to or greater than or equal to. Then do your correction for continuity by whatever makes your interval bigger. Okay. So now that we're at this step, we can find our probability just like we would any other normal probability. So we have our value, 66.5. So actually it's going to be x minus mu over sigma. My sign doesn't change. We have 66.5 minus our mu we said was 53, divided by our sigma, which we said was 4.99. And this is going to give us the probability of x minus mu over sigma, this is z, greater than or equal to 2.71. Now, once you get to this step, this works exactly the same way it has in any other prior sections we've done. So you look at this and you say, okay, well, I'm looking for the probability to the right on my standard normal of 2.71. But I can't look this up in my table. What do I need to do? I need to find the probability of the entire sample space minus what is to the left of 2.71, and that will give me my correct probability. So this is going to end up being 1 minus the probability z is less than 2.71. Now, by the way, once we're in terms of z, we're in the normal space, meaning that less than, greater than, really won't make any difference if it's or equal to. But because I'm doing the complement, I'm just trying to keep it precise because we were looking at everything to the right of, including 2.71. The complement of it is everything to the left of, not including 2.71. So in this case, we look up our probability of z less than 2.71, right? It's positive, it's to the left, we can look it up in our table. We go down to 2.7, we go over to 0.01, we get 0.9966. Which is going to give us a probability of 0.0034. For our next example, we're going to be using the same setup. We're asking 100 college students about their use of Google, and it's asking about what is the probability that exactly 67 say yes. Sorry, 57. Well, we already checked our assumptions, but the first step would be check your assumptions. NP, is it greater than or equal to 5? Yes. NQ, is it greater than or equal to 5? Yes, we can use our normal approximation. Now, I actually want to sidestep here for a second and talk about another method you could use instead of NP and NQ. If you have a word problem and it gives you the number of respondents that said yes and no, you can actually look at, is this value, X for yes, is it greater than or equal to 5? And is the answer no, or the complement of yes, also greater than or equal to 5? And this is because, let's say that I said, instead of 53% of students said yes, I said out of the 100, 53 said yes. So I have an X of 53. And then I need to figure out, what is my probability? Well, my probability would be the number of people who said yes, that would be 53, over the total number of people that I asked the question to. So this would be 53 over 100, which would be 0.53. And then when I do NP, what's going to happen? I'm going to take that probability for my P. I'm going to use 100 for N. So I'm going to get 100 times 0.53, and I get right back to 53 respondents. And that's actually what you're finding when you're doing NP and NQ. You're looking at, based on the sample size that I had and the probability of success or failure, what is the number of expected people that would say yes in this case or no? So if you already have it in terms of that data, if I told you instead of saying 0.53 people said yes and 0.47 said no, instead if I said 53 said yes, 47 said no, or even just 53 said yes because I know the total number that I asked, you would just have to say, okay, well, do I have more than 5 respondents that said yes? Good. Do I have more than 5 respondents that said no? Good. In which case you could also use that. Okay, back to our problem. So looking at our steps, we checked our assumptions, and the first step we always talked about when doing your probability is get it in terms of or equal to. Well, guess what? It is equal to. So we've got the equals to already covered. So now what we're going to do is we're going to have to do our correction for continuity. Now, if you remember, our correction for continuity is that we take this value, 57, and we subtract 0.5. So this is going to be 57 minus 0.5 is less than or equal to X, which is less than or equal to, we take our 57 and we add 0.5. So this is going to end up being 56.5 is less than or equal to x is less than or equal to 57.5. I forgot my p. So now what we're going to do is we are going to do our z transformation. So this is going to be 56.5 minus 53, that was our mu, divided by 4.99, that was our sigma, less than or equal to x minus mu over sigma, less than or equal to 57.5 minus 53 divided by 4.99. And this is going to give us the probability of 0.70 is less than or equal to z is less than or equal to 0.90. And like I said in the last problem, once you get to this step, you're just solving it like you would any other normal probability. So we're going to take the probability that z is less than 0.90, the larger value, minus probability of z less than the smaller value, 0.70. For both of these, they're positive values. Both of them are looking to the left. So therefore, we can look both of these up in our table. So the probability that z is less than or equal to 0.90, we go down to 0.9, go over to 0.00, we get 0.8159, minus, then we go to the probability of getting z less than 0.70, so we go to 0.7, go over to 0.00, we get 0.7580. Which is going to give us a probability of 0.0579. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.